All right, hey everybody, chapter 2, this is lesson C, part 2 on power functions. So power functions are related to polynomials that we've been studying so far, except power functions only have one term. So we're going to define a power function, and then we're going to apply some direct and inverse proportionality to some word problems. So it should be a pretty brief lesson. Let's go ahead and get started. So here we have a power function, which is a function that comes in the form given below. It'll come in the form f of x or g of x or whatever it might be with an independent variable where we have a, x to the nth power, where a and n are non-zero real numbers, n is called the power, and a is called the constant of variation. So this form right here is called a power function. So it's like a polynomial except it doesn't have multiple terms. So n could be any number though. Specifically, when we talk about monomials, which we'll get to later, n must be a positive integer. So numbers like 1, 2, 3, 4, 5, 6, etc. So let's take example 1 here and identify whether the following are power functions based on its definition above. If they are, state the constant of variation and the power. C, K, and G can be considered constants in each of these situations. So let's look to see if A and N are non-zero real numbers. So it looks like N, our power, is going to be 3, right? This 3 right here. Whereas our constant of variation, COV, constant of variation, will be 4 pi over 3. Okay, so yes, this would be a power function. In the second example, I'm going to expand this slightly using some rules of exponents. Okay, I would have g, which is a constant, times 3 to the 5 halves times x to the 5 halves, or I could say square root of x to the 5th. I'll put x to the 5 halves. So this number here, 5 halves, is our power. So n, our power, is 5 halves, which is a non-zero real number. So we've met all of our specifications so far. Our constant of variation is g times 3 to the 5 halves. I don't know what g is, but provided it's a real number, we're good to go. So yes, this would also, based on this form, be a power function. Okay, in the third example, what we see, let me rewrite this slightly. F of x, oops, I don't have an x here. Let's call this f of h. Okay, f of h is equal to 2k cubed over g squared h squared. Okay, so I'm going to rearrange this slightly because my independent variable is h and it's squared. I'm going to rewrite f of h as 2k cubed over g squared times h to the negative 2. So it looks like my power is negative 2, which is a non-zero real number, and my constant of variation is 2k cubed over g squared. Okay, on to example number 4. It looks like if this is an expression or an equation function in terms of x, x is raised to the 0 power, which is a problem, right? Because we need a and n to both be non-zero real numbers. Since n equals 0, no, this is not a power function. Okay, and I could kind of breeze through here, but I could say in number 5 that n is negative 5 halves. That's the exponent on x. And our constant of variation is 2 pi k. All right, so yes, this would be a power function. All right, the last example is surface area. That's actually, if you don't remember, that is the surface area formula for a cone. Since there are 2 terms, this is not a power function, right? It should be a single term in that form. Okay, so there you have it. That's some basics on power function. Let's move on to using this in both a direct proportionality and inversely proportional situation. So power functions come in two forms, monomials and non-monomials. Okay, in a monomial, the requirement or criteria is that a is a non-negative integer. So that means that a has to be an integer, meaning it has to equal either 1 or 2 or 3 or etc. Whereas for a non-monomial, a could be anything else. So for example, in number 1, if our independent variable is c, then our constant of variation would be m, and our power would be 2. Okay, so k is real, right? That's our constant of variation. And n is 2, which is a non-negative integer. So that would be an example of a monomial. Likewise here, it looks like x is raised to the power of 0. So therefore we would have a constant of variation of 29 and a power of 0. So that would also be a monomial power function. Okay, so in number 2, let's see why these are not monomials. Well, in this case, it looks like n is equal to -6, which is negative, so that breaks the non-negative rule. And in number 2, it looks like n equals 1/2, which is not an integer. Therefore, neither of these would be monomials. So I did make a mistake on the last page. I think I said that the fourth example was not a monomial. It is a monomial. I think it was something like m of x equals 91c. And because x was to the 0 power, that's okay. N has to be in order to be a power function, n has to be a non-negative value, right? And so therefore, that would, yes, be a monomial, and the constant of variation, or excuse me, that would be a power function, and the constant of variation would be 91c. Just wanted to make that correction before I got too far ahead. Okay, let's go on to direct and inverse proportionality. Okay, so direct proportionality, a function f of x is directly proportional to its independent variable x if the ratio of the two quantities is constant. So let's say that I have f of x equals 9x squared. Hold on, let's go 9x. Well, if I divide it by x, then the ratio of f of x over x is equal to 9, right? So that's a constant ratio. All right, that's an example of how you would see this constant come up. Okay, so now k in that case would be 9 and a would be 1, right? Because x is to the first power. So what we're going to do is we're going to write a statement, each statement as a power function using k for the constant of variation if 1 is not provided. So think about this now. The area of an equilateral triangle varies directly. That's the same as direct proportionality. Okay, so these two are synonyms or phrases that mean the same thing. Varies directly and direct proportionality. If we were to use the word proportional, that would also work. You'll see that in the next example. So area is directly proportional. If I don't see a k value thrown in there for the constant, I just throw k in as the square of its side length. So there's a direct proportion related there. So the area divided by side squared is always going to be the same constant. That's why we call it directly proportional. Now the energy E produced in a nuclear reaction is proportional to the mass with a constant of variation of c squared. So E equals c squared, which is our constant, times m. Okay, direct proportionality relationship here, where it looks like our power is 1. This is m to the first. Okay, and our constant of variation will be c squared. Okay, let's move on to inverse proportionality. Inverse proportionality. A function is inversely, that should say inversely. My bad on the notes there. Inversely proportional to its independent variable if the ratio of the two quantities is inversely related. Well, that was helpful. But what you're going to see is that A now is no longer a positive value. It's going to be a negative value. So let's write a statement. Each statement has a power function equation using K as we did before. So the height h of a falling object varies inversely as the square of the time it has been falling with a constant of variation of negative 16. So what we would say is that the height is equal to the constant of variation times t squared, t to the negative 2. Okay, so the height is equal to negative 16 if I were to rewrite over t squared. Let's look at number 2. The force of gravity on an object, G, is inversely proportional to the square of the distance from the center of the Earth. I'm not given a constant of variation, so G is equal to K over d squared. Okay, so if you're to take anything away from today, right, when we talk about direct and inverse proportionality, they both take on the same form, right? So let's say y is directly proportional to x cubed, or y is inversely proportional to x cubed. Okay, the only difference between the two is the power sign. So with inverse proportionality, our power will be negative. With direct proportionality, our power will be positive. This kind of fits in at an awkward spot. It is kind of a polynomial. It's just a monomial, although direct proportional situations are monomials. Inverse proportional are not monomials because this is a negative power. But just something good to be aware of. You'll be tested pretty lightly on this topic, but it's something that you will see come up in calculus in future years. So, hope it went well. Let me know if you got questions about direct and inverse proportionality as well as power functions, and we'll see you in the next video.